All right, good afternoon, everyone. So we're going to be going through an example of how we can calculate the internal member forces in this truss system using the method of joints. So this is a truss system that we constructed in class on Tuesday, and we were able to calculate the reaction forces in the X and the Y directions for joint A, and the reaction force at joint D in the Y direction. And those values are listed over here. We'll be needing these for our examples in calculating the individual member forces within this truss. Now, this is going through the concept of either tension or compression that is going to be specific to each of the members in the system. Every member in the system is going to have either a compression or a tension force. So remember, for tension, the member is experiencing this outward pull. And keep in mind that we're going to be using the method of joints. So we're really going to be looking at what is going to be happening in terms of an opposing force that happens at the joint. Because if the member is in tension, then the internal components of that member are pushing outward. And so from the joint's perspective, it's going to meet this push outward with an equal and opposite force, pointing in toward the member. Same thing with compression. The compression for a member in the truss system means that the internal components are going to be pushed together. So if the member is experiencing compression, then at the joint, it's going to experience an equal and opposite force going in toward the joint. And for this method of joints, we're going to assume that all of the members are in tension, as in any of the forces that we're going to write down are going to be pointing away from each of our joints. So keep that in mind as we draw the free body diagrams that go along with joints A, B, C, and D. So what we're going to first discuss are the equilibrium equations. These are going to be a huge component in our method of joints problems. So we first have the sum of the moments being equal to 0, the sum of the forces in the X direction being equal to 0, and the sum of the forces in the Y direction being equal to 0. Now, the moments we were able to use to calculate the reaction forces at each of our supports, our pinned support here at joint A and our rolling support here at joint D. So the good news is when we're calculating the internal components or the internal forces in our system, we don't really need to know the moment forces. All we care about are the forces in the X and the Y direction at each of our joints. The other things that we do need to know in order to calculate the individual truss member forces, we need to know the angles at A and D. And so this is a basic review of trig, that sine of my angle, whatever angle that I choose, is the ratio of the opposite side to the hypotenuse of the triangle. Cosine of theta is equal to the adjacent side divided by the hypotenuse. And tangent of my angle is equal to my opposite side divided by my adjacent side. So for calculating theta 1 and theta 2, I can acknowledge the adjacent and the opposite sides here. Notice for theta 1, my opposite side is 15 feet. My adjacent side is 8 feet when I'm considering this right triangle. And so when I'm calculating theta 1, I remember, use inverse tangent. When I type this in, I get 61.93 degrees, being the measure for angle 1. For angle 2, it's the same hat and dance. The tangent of theta 2 is 15 feet divided by 13 feet. To calculate the angle, I take the inverse tangent of that ratio to get 49.09 degrees. So these are going to come into play especially for joints A and D. So now we're going to hop to the method of joints. And I'm going to start with some of my easier joints here, joint A and joint D. And the reason I'm doing that is because they don't have as many members attached to the joints as C and B. So when you're starting these truss calculations, start out with an easier joint. So I'm going to first draw the free body diagram at joint A, because I want to understand how all of the forces in the X and the Y direction are interacting with one another. So I'm going to draw joint A here. I have my line segment here, and I'm going to represent that as AC. So I'm starting at A, ending at joint C, so I'm calling the line segment AC. In the same way, I have AB. And notice that I'm drawing my arrows outward from joint A because my members are experiencing a tension force. Going from here, I have theta 1, so I'll just go ahead and label that theta 1 just so that I know that this is going to be the value of 61.93 degrees. And in addition to that, I have these other forces that we diagrammed back in the previous example during class. So we have, in the same direction as AB, we have the reaction force of A in the x direction and the reaction force of A in the y direction. Sorry about that. Let's clean that up a little bit. Reaction force of A in the y direction. Okay, so we have that all mapped out, and to help us out with the truss calculations, I'm going to make a little T-chart. So the sum of the forces in the x direction, I'm going to list all of those out. I'm going to also list out the sum of the forces in the y direction. And remember that the sum of the forces in both directions have to be equal to 0. And I'm going to write down the forces, and I'm going to list out the unknown values at first. So the sum of the forces in the x direction, I have the force of AB, and it's strictly going in the x direction. I also have the reaction force of A in the x direction. And I know that that value is equal to 0 pounds, but I'm going to go ahead and list it out anyway, just so that I can make a notation as to, yes, this force is going in the x direction. And I also have a component of the line segment AC that's also going in the x direction. So notice that whenever we have a diagonal member, that it's going to have both an x and a y component. And specifically, we've mapped out this truss system in such a way that the portion of AC that's going in the x direction can be calculated by AC cosine of theta 1, which works out really well for us. So we have the sum of the forces in the x direction being AB plus the reaction force in the x direction plus AC cosine of theta 1. Now for the y direction, we have the reaction force of A in the y direction plus the y component of line segment AC, of member AC. And that's going to be mapped by AC sine of theta 1. Now for a better understanding as to how I'm getting the cosine and the sine values, let's draw a little triangle down here. AC, if I'm drawing this line segment, consider the right triangle that's formed. So we have line segment AC, and we have angle theta down here. Call it theta 1. So by definition from the trig functions up above, if sine of theta is the opposite side divided by the hypotenuse, then I can rewrite the opposite side here as the product of the sine of my angle multiplied by AC. So this is AC sine of theta 1, and this is AC cosine of theta 1 by the same logic, because cosine is the adjacent side divided by the hypotenuse, so I can rewrite my adjacent side as a product of my hypotenuse and cosine. Okay, so now consider this. We want to solve for the values of AC and AB. That's our whole goal, is to be able to map out what the value of AB is as a force and what the value of AC is as an internal force. So let's consider the unknowns. I don't know AB and I don't know AC. So in the x direction, I have 2 unknowns. In the y direction, I have 1 unknown value. Remember, we figured out the reaction force of A in the y direction previously. So I'm going to take the forces in the y direction. I'm going to solve that first. So the reaction force of A in the y direction was 154.76 plus AC sine of theta 1, which we talked about being 61.93 degrees. Now if I'm solving for AC, my unknown, going to start by subtracting 154.76 to the other side. So we have AC sine of 61.93 equals negative 154.76. Dividing both sides by sine of 61.93, I have AC equals negative 154.76 divided by sine of 61.93. And the value that I get there is negative 175.39. I'm going to round to the nearest hundredth. And remember, my units are in pounds. So I have the value of AC, and I'm going to update my chart up here. So I'm going to write negative 175.39 pounds. So that's the compression force that's occurring between A and C. Now that I have AC, I can go back and I can take this value and plug it in to the sum of the forces in the x direction to solve for AB. So I'll label this as a 1, saying we did that first. So the second thing that we did, we're going to write AB plus the reaction force of A in the x direction. And we know that that's equal to 0, so I'm going to get rid of it. And then plus AC, so it's negative 175.39 times the cosine of theta 1, which was 61.93. And I know that has to be equal to 0. Now I'm going to go ahead and add this to the other side of my equation. So AB equals 175.39 cosine of 61.93. If I were to type that into the calculator, I would get, let's see, give me a sec. So I get 82.53 pounds. And then I can update my chart up here. So the internal force of joint B, or of line segment AB, is the positive tension force of 82.53. So I've got